So hopefully in the last video when we introduced examples of vector fields, hopefully you felt like that it felt familiar somehow, maybe a little bit of deja vu, and that's because you've actually seen vector fields before. And so we've been studying specific kinds of vector fields called gradient vector fields, and that's just the gradient of a regular function actually produces a vector field. We'll see examples of these in a minute. So I went ahead and separated the two-dimensional case and the three-dimensional case, but it's just the gradient. It's not a big deal. So those actually do produce vector fields as well. I do want to mention some notation. So we're going to call functions like this, f of x, y, maybe z equals x, z squared plus 2z. We're going to call this a scalar function because even though you plug in three variables, x, y, and z, you get out a scalar, right? So these are scalar functions, our old familiar friends that we've been working with, whereas we're going to call these guys vector functions. So the gradient vector field, I should say a gradient vector field, it's just the gradient of a scalar function. And I wanted to remind you that the gradient is perpendicular to the level curves or surfaces, depending on how many variables you have, right? It's either a curve or a surface. The gradient of f is perpendicular to the level curves, surfaces of your scalar function at any given point. So that's a really important trick to keep in mind. We use that a lot. So I want to give vectors fields a name when they are the gradient of something. So we're going to call a vector field big F conservative if big F is the gradient of some scalar function little f. So in this case, little f, the scalar function, is called the potential function for big F. Now, I promise you there's nothing political in this title whatsoever. I'm not sure what inspired it, but it is what it is, and it's been around a long time. So I'll try to avoid any political jokes as we go along. It just happens to be the name of vector fields who are the gradient of some scalar function. And so I want to make a very important remark. I've even used red here. Not all vector fields are conservative. So there's lots of vector fields that cannot be written as the gradient of some scalar functions. So let's do a quick example, and then we'll come back and we'll do a little bit longer one in the next video. So this particular vector field right here, this is conservative. Why is it conservative? Well, since you can write big F as the gradient of little f, where let me erase that, where little f of xy is x squared y. And you can check this in your head. If you take the gradient of little f, the first component is going to be 2xy, the second component is going to be x squared. So easy to see that this one is conservative when you've got this potential function in front of you. Maybe if we didn't show you that, it would be a little harder to come up with that. So that's actually what the next video is going to be about, is how do you come up with a potential function when you're not given it. So I'll end this one here, and then we'll go on to the next one.